This diagram illustrates a global supply chain network struggling under the weight of a specific failure, a $2 trillion global inventory mismatch. We often assume this waste is diffused across millions of small businesses, but the reality is concentrated. It is common for a single large enterprise to carry $700 million in mathematical planning errors on its books at any given time. While it is tempting to blame human error or unexpected disruptions, these planning gaps are built into the processing time of the software itself. The delay is a direct result of compute latency. To run basic supply and demand equations globally, legacy enterprise software can take up to 17 hours to complete a single compute cycle. In modern commerce, consumer demand and supplier availability fluctuate by the minute. A 17-hour delay means that by the time a macro-level supply chain plan is finally generated, the micro-fluctuations on the ground have already changed the landscape. Human planners cannot bridge a 17-hour gap by working harder in spreadsheets. The monolithic software architecture used to manage these resources is unable to operate at the speed of the data it receives. The current industry trend is to take a generative AI chatbot and place it as a wrapper over an Excel sheet or a legacy ERP. But probabilistic language models cannot solve deterministic operations research problems. Solving this requires moving beyond the ERP model toward an agentic supply chain architecture. In this context, an agent is an autonomous single-task software entity. It is designed to execute focused optimizations in real time, reacting to data the moment it is recorded. This changes the role of the human planner. Instead of manually creating plans and validating spreadsheet math, the human becomes a curator, defining the strategies and supervising the agents that execute them. The goal of this architecture is to eliminate the batch processing delay entirely. By removing manual data entry and software bottlenecks, the system is designed to close the gap between a disruption occurring and a solution being deployed. To make this work, we have to acknowledge the reality of modern enterprise data. It is trapped in isolated silos like CRMs, PLMs, and ERPs. This architecture diagram shows an agentic OS, an orchestration layer positioned above those fragmented systems. Within this layer, we deploy specialized agents dedicated to demand, supply, and finance. But agents are useless without communication. The gap is bridged by the Model Context Protocol, or MCP. It acts as a universal standard, allowing agents to access legacy data and talk to one another. In practice, MCP allows a demand agent to instantly discover the capabilities of a supply agent and request data without waiting for a human to route the inquiry. MCP allows these individual software tools to function as a communicative system, enabling the enterprise to react as a single coordinated entity. We can see how this operates under pressure through a shortfall scenario. A critical system alert flags that the enterprise is short 4,000 units for a high-value product, the Titan AI Accelerator. Instantly, the demand agent assesses the order backlog and identifies a $4.2 million revenue risk attached directly to this specific shortfall. The supply agent responds via MCP, bypassing human planners to directly query real-time telemetry from the manufacturing plants. This topological map displays what the agent finds at the manufacturing node. A vibration in a lithography machine has caused the production yield to drop from 95% to 87%. Instead of a human spending hours modeling workarounds in a spreadsheet, a simulation engine autonomously spins up. The agents rapidly execute 123 different recovery scenarios. They isolate the optimal solution, a direct distribution center to distribution center air freight transfer, bypassing the bottleneck and recovering the $4.2 million. This entire process, diagnostic, simulation, and routing execution, happened in under 60 seconds, with zero manual spreadsheet intervention. At this point, it is worth asking, why couldn't a standard off-the-shelf large language model just calculate that optimal air freight route? The limitation is built into the architecture. LLMs are probabilistic language engines that simply predict the next word. This makes them flawed at deterministic operations research. Supply chain routing is a variation of the traveling salesperson problem. It requires strict mathematical heuristics, not natural language reasoning. When organizations rely on an LLM to perform pure math, they end up with inventory plans that look correct in text but fail in physical execution. To truly optimize a $2 trillion problem, you don't just need agents that can talk to each other. You need underlying mathematical algorithms that can evolve. This brings us to Alphaevolve, a system designed specifically for complex, open-ended mathematical optimization. This interface shows two components. On the left, a seed algorithm. On the right, a human-defined evaluation function setting goals like minimizing latency. Alphaevolve mutates the seed code, autonomously exploring the mathematical problem space without human engineers. The system continuously tests these mutations against the human's evaluation criteria. It discards the failures and iterates on the successes. We have seen the proof of this in the logistics sector. When applied to FM logistics, this evolutionary process yielded a 10.4% routing improvement. In the legacy environment, identifying and coding a 10% algorithmic improvement manually requires an engineering team months of trial and error. The human no longer writes the optimization code. They define what better looks like, and the system evolves the math to achieve it. But how do enterprises prevent autonomous self-evolving agents from making catastrophic multi-million-dollar errors? This macro-level architecture map illustrates the solution, a top-level governance layer known as model armor. Human curators use model armor to continuously monitor agent interactions, set hard boundaries on execution, and prevent malicious or hallucinatory behavior. Governance also extends to the data infrastructure. Evolutionary algorithms cannot fix data pipelines that are already corrupted. The rule of garbage in, garbage out remains. Agents require direct access to a unified master ledger to maintain low latency, rather than relying on slow API middleware that delays decision-making. This infographic outlines the required deployment framework. Organizations must establish clean data, target a single high-value problem, and only then scale fast. Attempting a massive rip and replace of legacy ERPs will fail. Technical leaders must isolate a single mathematical error, prove the Agentic model works in that instance, and use those verified results to justify scaling across the enterprise. Supply chain superiority in the next decade belongs to organizations that abandon 17-hour legacy compute cycles. Instead, they must let their algorithms evolve, elevating their human planners into the ultimate orchestrators of true global autonomy.